I hope I did not kill you yesterday with mathematics of persistent homology. Today, we are going to study the most important and the most famous result in persistent homology, and it is called stability. So this will be the last theoretical course of this summer course, and tomorrow we will do a tutorial and apply all of that with real data sets. So we have seen yesterday that these thickenings we consider, these filtrations, can be associated with a barcode, and the barcode reflects the homology of our space, our thickenings, and moreover, these barcodes tells you how the homology persists. Okay. So in theory, we could have considered this construction, this thickening construction, with a nice circle. So the thickenings of the circle gives you annulus, all right? They are all topological circles. And the barcode of this filtration is very simple. It's only 2 bars, 1 bar in H0, representing the connected component, the zeroth homology feature of this annulus, and 1 bar in H1, because all along the filtration, we have a circle, topologically. We have 1 cycle in H1, and the cycle dies at the value 1, the radius of the circle, where we obtain a ball. But in practice, we are not given this nice circle, but a point cloud, potentially noisy. We still consider its thickenings, and what we get is a barcode where we can still read the homology of the circle, right? We have to look at the large bars. They represent interesting, valuable information. For instance, this large red bar or this large green bar. And the little bars are seen as topological noise. Okay. So this is the question of today. How can we precisely, mathematically, explain this phenomenon, right? That even with a noisy data sets, we can read on the barcodes homological information. So first, we will have to define some distances between persistence modules, right? Then I will tell you about the isometry theorem that relates these distances. And we will conclude with the famous stability theorem. And at the end of this lesson, you will know everything about the basics of persistent homology. So there are 2 distances one defines on barcodes. The first one is called bottleneck distance. So I will take the same example all along this lesson. 2 barcodes, all right. The first barcode we will consider is this one. We have only 1 bar from 0 to 1. And the second barcode is this one, where you can see a long green bar and a lot of topological noise next to it. So barcodes are a multiset of bars, of intervals, right? We can describe these barcodes like a set of intervals. So in order to define the bottleneck distance, we will define first matchings, partial matchings. So the first barcode is called P, and the second one Q. A partial matching between P and Q is a subset M of the product of P times Q, such that if I have, all right, if I have a point, a bar P in the first barcode, I can have at most one bar Q in the second barcode, such that the tuple PQ is in M. Okay. And conversely, if I have a point Q in Q, there may exist only one bar P in P, such that the tuple PQ is in M. When I have such a partial matching, M, I will say that the tuples PQ in the matching are matched. The interval P and the interval Q are matched. Okay. And so this definition says that a bar interval may be matched with at most one other bar of the other barcode. Okay. So for instance, the empty sets, this is a partial matching where no bars are matched. This is another matching, another partial matching, where I match this long bar here with this small bar here, right? And the other ones are not matched. This will be another example of a matching. And one that will be interesting for us later is this one. I matched the long bar of the first barcode with the long bar of the second barcode. All right, all of them are partial matchings. Now we have matched bars, and the bars that are not matched by this matching, we will match them with their midpoint. Okay, if I take a point P in P that is a bar in P that is not matched, I will say that it is matched with the singleton midpoint of this bar. Okay, I will do a drawing. So here, P is equal to the interval P1, P2. So for instance, if this bar here were not matched, I will match it with its midpoint, 0.5. All right, up. This one goes with this one. So when we do that, we at the end matched all bars with another bar of the other barcode or with its midpoint. Okay. All bars are matched. And now I will define the cost of a matching. If I have a matched pair PQ, two intervals P and Q, I will define the cost of this matching as the subnorm of P minus Q. So here I see intervals as points of R2, and I consider the subnorm. So the subnorm of P and Q is the supremum of the absolute value of the difference of their coordinates. Okay. And then the cost of the whole matching M, of the whole partial matching, is defined as the supremum of all these costs. Okay. So basically, if this green bar were matched with this one, so this subnorm is the difference between that and between that. Right? It is a supremum of the distance of their endpoints. And if my bar is matched to itself, to its midpoint, then the distance, so simply is the half length of the bar. Okay. I take the supremum of all the costs of the pairs, and I obtain the cost of a partial matching. Okay, this is the cost of one matching. Now I will define the bottleneck distance between the barcodes P and Q as the infimum of the costs over all the partial matchings. Okay, you look at all the partial matchings that can be made between these two barcodes. For each of them, you compute their cost. You take the infimum of the costs, and you get the bottleneck distance. So in this case, the best thing to do in order to obtain the optimal partial matching, we should match this bar with this one, because the cost of this pair will not be too high because they are quite close to each other, these two bars. And then all the small bars will be matched to their midpoints, but they are so small that their cost will be small too. Okay. So this is the distance between barcodes, and I can, thanks to that, define a distance between persistence modules. Say we have two persistence modules, U and V. So we've seen yesterday that if we can decompose them into interval modules, then we can define their barcode. And simply, we will say that the bottleneck distance between U and V is the bottleneck distance between their diagrams, their barcodes. So really, this is the idea behind, this is the introduction, behind saying that these two barcodes are close to each other, right? A good notion of closeness, a visual one, is the bottleneck distance. Is it easy to prove that this is a metric? So actually it's a pseudo extended metric. I will write that in the chat. Extended means that it can take the value plus infinity. This is because we may have infinite intervals, and these infinite intervals, if you cannot match them with infinite intervals in the other barcode, then we have infinite cost. So this is an extended metric, and it's a pseudo metric because you may have two barcodes with distance 0, though they are not the same. For instance, if you take the empty barcode and the barcode that contains only one singleton, an interval with only one point, their distance is 0, but they are not the same. So the only thing we can prove is that it satisfies the triangular inequality, and this is true. You can prove that by concatenating matchings. If you have 3 barcodes and 2 matchings, you can create a matching between the 2 end barcodes. But in practice, the fact that it's only a pseudo metric is not very important, because there is a way to so when we talk about barcodes, most of the time we see them up to singletons. So you can define a real extended metric on the space of barcodes up to singletons. Right. But in practice, we will, well, always have finite barcodes. And so finite values, finite intervals, and finite values of distance. Okay. So I would like here to study an example, a very simple one. What is the bottleneck distance between the barcodes P and Q that only contains one interval each? Okay. P will be the barcode that contains the interval AB, and Q A prime, B prime. So I have only one bar per barcode. So there exist only two matchings. Either the empty matching, I do not match the bar, or the non-empty matching where I matched the two bars, right? Let's start with the empty matching. So the intervals are matched to their midpoint, right? And what is the distance of any interval to its midpoints in the subnorm? It is its half length, right? I take the supremum of the difference between A and this, and B and this gives me the half of the length of the bar. Same for the other bar. So what I obtain is that the cost of the empty matching is the maximal value between the half length of the two bars, the two intervals. Okay, now the non-empty matching, where I match AB to I prime B prime, the cost of this pair is the supremum of the difference. So this is the maximum between A minus A prime and B minus B prime. Okay, I compute the difference between the endpoints of the intervals. So this is cost of M prime. And I can say that the bottleneck distance between P and Q is the minimum between this maximum, the largest length, half length of the bar, and this one, the difference between their endpoints. So, so what it really means, so either you are in the first case or in the second case. You are in the first case when you consider the maximal half length, when the bars are so far away that this is not interesting to match them. Let's say something like that. Here it is better to not match these two bars. So we get the first term. We get the second term. This is the minimum when the bars are close to each other. So when we have something like that. Here it is a good idea to match them. Okay. So we computed the bottleneck distance between P and Q. Now I can do the same with interval modules. Okay, consider the interval modules B, AB, and B, L prime, B prime. Okay, these are the interval modules corresponding to the intervals AB and L prime, B prime. We know that their barcode are the sets P and Q here. The barcode of an interval, the barcode of the interval module is the interval itself. So the bottleneck distance between these two interval modules is the bottleneck distance between their barcodes, and we computed that just before, and we deduce this formula. Okay. So this is it for the bottleneck distance. This is really a geometric, nice, understandable distance. Now we will define another distance, more algebraic, which will be very useful, and it's called the interleaving distance. All right. So this is not a distance between barcodes, but it is a distance between persistence modules. Consider two persistence modules, V and W. So a nice way to draw a persistence module is to write its vector spaces on a line, right? And the arrows, the connecting maps between each of these vector spaces, okay? Remember that I denote the map between Vs and Vt by Vst. The map between Vt1 and Vt2 is denoted Vt1, T2. Okay, same for W. These are my two persistence modules. First, I will define an epsilon morphism. Let's take epsilon, a real number, non-negative. An epsilon morphism is a collection of morphisms, right? From Vt to Wt plus epsilon, okay? I do not ask phi t to go in the same value of t, but a bit later, right? In W t plus epsilon. And moreover, I ask that these diagrams commute. Okay? Remember that commutativity of a diagram means that if I follow these two arrows, this must be equal to these two arrows. Right? In other words, phi t composed with Vst must be equal to Ws plus epsilon t plus epsilon composed with phi s. Okay.
We can't see anything, Raphael.
Oh. I will try again. Can you see something now?
Still no.
No? Still no.
No.
Well, I will write in the chat then. Oh, I know why. Do you see something if I do that?
Yes.
Okay, nice. Thank you. Thank you. All right. So I will say it again. Asking for this diagram to commute means that if we follow this arrow and then this arrow, we obtain this arrow and this arrow. Okay. So the compositions are maps from Vs to W t plus epsilon. So I will write that here. The first composition is phi t composed with Vst. And it must be equal to Ws plus epsilon t plus epsilon composed with phi s. Okay. If my collection of morphisms satisfy this commutativity for every value of s and t, then I have an epsilon morphism. Okay. The idea is that you cannot only ask for a family of morphisms because persistence modules have a structure. Persistence modules are not just a collection of vector spaces, right? This is a collection of vector spaces plus maps between them. This is how you track cycles. This is how you understand persistence. If I had only the morphisms, this would not be compatible with the persistence structure. So we need these commutative diagrams. Okay. Epsilon is any real number. Yeah. Yeah. Okay. Again, a definition. An epsilon interleaving. This is where it gets interesting. An epsilon interleaving between my persistence modules V and W. This is a pair of epsilon morphisms. I have two epsilon morphisms. The first epsilon morphism goes from V to W, and the second one from W to V. Okay? So I have two epsilon morphisms, and I want them to be compatible, and this compatibility can be expressed with, again, two commutative diagrams. Okay? So two epsilon morphism means that I have my persistence module V, my persistence module W. I have a first epsilon morphism here, phi. The second one up psi. And I want these commutativities up. Okay. Trust me for the moment. We will see very soon that this is a nice definition. When I have the existence of an epsilon interleaving, I will say that my persistence modules are epsilon interleaved. Up. In this case, the persistence modules are epsilon interleaved. And really, being epsilon interleaved means that they are close to each other. We will see that soon. And now I can define the interleaving distance between V and W. It is the infimum of the epsilons such that they are epsilon interleaved. Okay. I look at all the interleavings, I look at their epsilon, and I take the infimum value of these epsilons. And this is the interleaving distance. Again, you can show that this is an extended pseudo metric. Yeah, between persistence modules between, yeah. Okay. Again, I would like to consider this example. We will understand a bit more what these definitions mean. I have two interval modules, the one built from the interval AB and the other one from the interval A prime B prime. I represent them like that under the real line. So this is A, this is B, this is A prime, and this is B prime, okay? First, what is an epsilon morphism between them? So an epsilon morphism, this is a collection of maps from Vt to W t plus 1, t plus epsilon, with a commutative diagram, okay? Say I take T here, right, and say that this is epsilon. Remember that the interval modules are defined as follow. Above each point of the interval, you have the vector space Z over 2Z. And out of the interval, outside, this is the vector space 0. So, and the connecting maps here, right? The maps of the persistence module structure are the identity while you stay in the interval and 0 when you go out or in from the outside. So what does it mean to have an epsilon morphism? I have these arrows here, okay, which goes from Vs to Ws plus epsilon. And say first that we stay in the intervals. I have a Z over 2Z. Each of the 4 vector spaces are Z over 2Z, right? This map is the identity, and this map also. Up, I will. Yeah, so this map is identity, and this map also is identity. And I'm wondering what may be these maps phi S here and phi T. So suppose that, for instance, phi T is 0, okay? I will follow this commutative diagram. This composition here, up, up, this is the composition of the identity and 0, so it is 0. But if I commute, this composition here also has to be 0 by definition of commutativity. And this is 0 only if phi S also is 0. all right? So the fact that phi t is 0 implies that phi s also is 0. And this works the other way around. If phi s is 0, you compose the map and you obtain that phi t must be 0 too. Okay, and now what if, say, phi s is the identity? Up. Then I have a first composition here that is the identity, then the identity. So this thing is the identity. But the other composition must be also the identity, and this is true only if phi t is also the identity. Up. This is the implication. In other words, if I consider two maps, phi s and phi t, in the intervals, then one being the identity implies that the other also is the identity, and reciprocally, conversely, if one is 0, the other one is 0. Okay, so an epsilon morphism in between the two intervals may have only one possibility, one value between 0 or the identity. Okay, what happens now if I go a bit further and I go out of the interval? So what I get is that I obtain here a vector space at the end that is 0, okay, because I'm outside the second interval. But now it doesn't matter what is phi t and phi s, because this composition is obviously 0 because its codomain, its image is 0. And here, this must be 0 too. So I have, well, this diagram does not give me anything interesting. In this case, phi s and phi t may be different. Okay. Doesn't matter. Phi t has to be 0, sorry, because its image is 0. Okay. And the last example, if I'm here, well, this is the same thing. This composition is 0. So, and this one also is 0 because I have the 0 map. So phi t here must be 0, and phi s can be, well, what phi s wants to be. Okay, so really the only condition is this one. Well, and so what we deduce is that globally, this map phi s, phi t, there is two possibilities. Either they are all 0, or either they are all non-zero when they can be non-zero. Okay. So between two barcodes, there exists at most two epsilon morphisms, the 0 epsilon morphism and the identity where it can be identity epsilon morphism. Okay. So what about epsilon interleavings now? An epsilon interleaving is a pair of epsilon morphisms, all right? And we have new commutative diagrams. So they look like that, okay? This is the commutative diagram on the left and this one on the right. So I will only consider the case where they are in the bars because outside it's trivial, we have 0. So the first one here, what we have is vector spaces equal to z over 2z. This map above is the identity by definition of an interval module. And so I want the composition of these maps to be the identity. Okay. But these maps, phi t and psi t plus epsilon, are either 0 or identity. if I want the composition to be the identity, there must be both identity. Okay. So I deduce from the definition of epsilon interleaving that here I must have the identity and here the identity. Okay. And this is also the case in the other direction. So at the end, all right, what I obtain is that an epsilon morphism, an epsilon interleaving must be composed by identity maps where it can. Okay. And so these diagrams can happen, all right, if I stay always in the barcode. So epsilon here must not be too large, because if epsilon is too large, I will go out of the intervals and I will compose a zero map. This would not give me the identity. So what we deduce is that the endpoints of the bars must be closed, or the bars themselves must be small. And so if you write that down, you will see that the interleaving, the only possibilities you have give you this value of interleaving distance, the maximal value between the half length of the bars, and the maximal value between the difference of the endpoints. And then you take the minimum of these values. Okay. And of course, you observe that this is exactly the bottleneck distance between these two interval modules. Okay. So this is not by chance. It is something we will study in the next section. Okay. Isometry theorem. It is stated here. Consider two persistence modules, U and V. Suppose that they are interval decomposable. Okay, so we can consider their barcode and their bottleneck distance. In this case, the interleaving distance between the persistence modules is equal to the bottleneck distance. Okay, these two distances we defined, which seem very different. One is more geometric, one is more algebraic. They are actually the same. They represent the same distance. And so this is very important, and I will show you a consequence of this result on the last section of today's lesson. And this will be the stability theorem. But for now, we will only study this isometry theorem. And so this is really algebra behind. It decomposes in two parts: the stability part, which says that the interleaving distance is greater than is not lower than the bottleneck distance, and the converse stability that says that the interleaving distance is not greater than the bottleneck distance. Okay. And so actually there is one direction which is way more easy to prove, and this is the converse stability part. Okay. So this is what we will prove. First, we want to prove that the interleaving distance is smaller than the bottleneck distance. Okay. So how do we do that? First, of course, I will decompose my modules into interval modules. It will be easier to deal with the interval decomposition. So V can be written as a sum of the interval modules with intervals I, where I is an interval in big I. Big I is its barcode. And same, W is the sum of interval modules. Now we'll consider a partial matching, okay, with cost epsilon. From this partial matching, I want to build an epsilon interleaving. So how do I do that? First, remark that this partial matching either match bars of the first barcode with bars of the other barcode, or it match bars with its midpoint. Okay. First, consider bars that are matched between the two barcodes. Okay. What we know is that as this is an epsilon matching, the endpoints of the bars must differ at most by epsilon. Okay. A minus A prime lower than epsilon, and same for B. But now, this is really easy to build an epsilon interleaving between two bars, two interval modules that are at most distant from epsilon. This is what we've seen a few slides ago. You simply define the identity maps where they can be, and the other maps are 0. Okay. So we can define an epsilon interleaving between the the interval module over I and over J. And I will denote this epsilon interleaving phi AJ and psi AJ. Okay. Now we have to study the bars that are matched with their endpoints. But these bars are with length smaller than 2 times epsilon. Okay. And on these bars, I will define the 0 epsilon interleaving. Okay. Because if I have a bar of length at most 2 epsilon, and say the 0 persistence module, the epsilon interleaving, I can define epsilon interleaving where all the maps are 0. Okay. Basically, this is because okay, let me draw something. Yeah, I will go here. If the bar is too small, or if epsilon is too large, let's say I start here, epsilon will do something like that, and then something like that. So I will always get out of the interval. So the commutative is very simple to prove because I have 0, so I can put the 0 maps here. Okay. This will commute. Okay. So at the end, we defined a lot of epsilon interleavings between bars of different barcodes or between bars bars alone, and we put the 0 interleaving. All right. So now, how do we define a global epsilon interleaving between the 2 persistence modules? We just take the sum of all these epsilon interleavings. Okay. Phi overline bar, phi bar will be the sum of all the phi ij for matched bars ij, and the sum of all the phi I0 for the bars who are matched with their midpoint. And similarly for psi. Okay. So if you write down the definition, you see that this pair overline phi bar, psi bar is an epsilon interleaving, and we deduce that the interleaving distance is smaller than epsilon. Okay, and epsilon was the cost of the matching we choose, and we could choose any matching. So at the end, we obtain that the interleaving distance is lower than the bottleneck distance. Okay. So really, okay, this is a bit tricky to understand when you are new to these notions of interleavings, but really there is nothing interesting here. It's just writing down definitions and composing trivial interleavings. Okay. This is very direct. Though what is less direct is the stability part. And really this is seen as some point of the theory, a place where, okay, all right, we have to do something a bit, I mean, it's more difficult than the rest. There exists not many proofs. I guess at least 2 or 3 different proofs of these facts, the stability result. And all right, I mean, you can read these proofs, it's nice. One of them is about 80 pages, but it's, well, you can read that. So yeah, we won't prove that today. I will just give you an idea. First, a question of Tiago. Can you give some intuition on the epsilon interleaving definition? For instance, what is the meaning of taking epsilon big or small? Okay, I can. So okay, let us look at first these commutative diagrams, okay, the epsilon interleaving commutative diagrams. So say we have 2 bars, okay. The commutative diagrams were, okay, Vt Wt plus epsilon. I hope you can see what I'm drawing. Yeah, thank you. Okay, so this under is the commutative diagram that is asked for every value of t. So here is the maps of my interleaving. So first, imagine that epsilon is very large. Okay. So I will go from here Vt to Vwt plus epsilon with large epsilon. Okay. Say that epsilon is this length. Okay. Up. This will be the map phi t. Okay. And here I'm in Wt plus epsilon. And the map psi t plus epsilon will be also this large. So if epsilon is very large, each time we will consider this diagram, we will go outside the interval j here. Okay. And if we go outside, what we have here is the 0 vector space. Okay. And also, on the right, we also have the 0 vector space. Okay. So this map here is 0. This is not the identity. This is a mistake that I wrote.
We can't see now.
You cannot see anything?
And since you changed your when you alt tab, we couldn't see anymore.
Oh, I didn't change anything.
Try to, yeah, now we see. Now we see.
Okay. Does my mouse is around VT?
Yeah. No, we can't see. It's very weird.
Oh, well, okay. I will. Can you still see the drawing?
No.
Ah. And now?
Now we can see.
Okay, I won't move. So I hope you can understand what I drew. Basically, if epsilon is very large compared to the intervals, these maps, the map between Vt and Vt plus 2 epsilon will be 0. Okay? And if the map above is 0, it doesn't matter what are the maps phi t and phi t plus epsilon. Okay? So it's very easy to create an epsilon interleaving when epsilon is large. You can take the trivial interleaving. Okay. Now, let us study the case where epsilon is not too large compared to the bars. Oh, right. Okay, something like that. Tell me if you cannot see what I do. Say epsilon is small. So my maps will look like that. Vt plus 2 epsilon, Wt plus epsilon. So in this case, above I have the identity map. So if I want this composition here to be equal to the identity map, these two maps, the maps of the epsilon morphism, of the epsilon interleavings, must be the identity, okay, must be non-zero. But in this case, if I want these maps to be the identity, I have to be a non-trivial vector space. I have to have a non-zero vector space here, okay? Because if I had 0 here, the maps here will be 0, and this composition will be 0, which is not the identity. Okay. In other words, if I have considered two bars like that, if the bars are too far from each other, up. Here I will have the 0 vector space. And so I would not be able to define maps here that will give me the identity above. So if the maps, so yeah, I will try to summarize that. If you take large epsilon, then these diagrams are trivial, okay, because we go out from the intervals. If you take a small epsilon compared to the length of the intervals, then we have to make sure that the bars are close to each other. Okay. Otherwise, we could not satisfy this commutative diagram because we would not have a non-zero vector space here. Does it make a bit more sense? Okay, awesome. Another question, what does small epsilon or large epsilon mean in practice? For instance, if we have a sample over the circle, a very good question, and I will keep that secret for the last section of today, which is in 5 minutes. We will link the epsilon of these interleavings with the proximity between the circle and our sample. Okay, really, epsilon at the end will be a distance between these subsets. Yeah. Okay, let's continue. I was saying that there is this stability result that is more difficult to prove. And this is interesting that it is difficult to prove. I will present one strategy here. It uses, so basically, when you want to prove the stability theorem, you suppose that the interleaving distance is small, and you want to prove that the bottleneck distance also is small. Okay, so take an interleaving, an epsilon interleaving. You want to build an epsilon partial matching, but how do you build a matching from an interleaving? A matching, this is an algebraic notion, and it does not really behave well with the bars, because a matching may, interleaving may mix the bars together, or well, this is not easy to do. What is more easy to do is, okay, if epsilon is really small, if your persistence modules are really close each other in interleaving distance, then you can understand what happens between the barcodes. Because if you change a little bit a persistence module, in the barcodes, the only thing you can change is moving a little bit the bars or creating small bars. Well, in other words, if the persistence modules are close in interleaving distance, you know how to prove the stability. But even only for very small values. And to go from small values to the actual value of the interleaving, you can use that, the interpolation lemma, that I think is quite pretty. It says that if I have two persistence modules that are epsilon delta interleaved, okay, I can build a family of persistence modules indexed by t between 0 and delta, where the first one, u0 is u, the last one, u delta is v, and you have that for every s and t in 0 delta, the interleaving distance between us and ut is lower than t minus s. Okay? So this is an interpolation between two persistence modules. We can build a collection, a segment, geodesic, some kind of curve in the space of persistence modules. Okay. And so now we can study the distance locally. And so we have something which is called the box lemma, which basically says that the stability is true locally. And if the stability is true locally, thanks to this interpolation lemma and using the compacity of 0 delta, we deduce that the stability is true for the actual persistence modules. So this is the idea. The other famous proof is one from Bauer and Lesnick. Basically, they are able, from an interleaving, they are able to build a matching. And this is very nice because here in this proof, we only deduce the existence of a matching, but we cannot see how it looks like. With this proof, we can see it. Okay, so this is it for the isometry theorem. Remember, interleaving distance and bottleneck distance are the same. The bottleneck distance is a distance that people use in practice because it's really a distance between barcodes. We see what happens. The interleaving distance is much more of a tool to study the persistence modules. And now, okay, only a few slides left. Before stating the stability theorem, I want to tell you this story. So follow me. We will try to build the stability theorem. I start with two subsets of Rn, okay, X and Y, and I will consider their Hausdorff distance that I denote epsilon, okay? X and Y, you have to see them as a nice shape and a sample, a noisy sample of it, okay? So what do we do? We will build the thickenings of these subsets, right? If epsilon is the Hausdorff distance, this was an exercise I gave you. You can show that X is a subset of the epsilon thickening of Y, and Y is a subset of the epsilon thickening of X. Okay. If I thicken a bit Y, I can put X inside, and same conversely. And this is true actually for every value of T. The T thickening of X is a subset of the T plus epsilon thickening of Y, and vice versa. Okay. So now, here, I write all the thickenings of X. I write only, well, the xt plus 2 epsilon, xt plus 4 epsilon, but you can imagine that on this line, you have all the thickenings of X, okay? And I denote also the inclusions between these thickenings with this arrow here. Under X, I put Y, same idea. All the thickenings of Y are here. And now, these inclusion maps between xt and yt plus epsilon, I can draw them on my diagram, okay? So we have something like that. This inclusion, I write it as an arrow, okay? Because yeah, this is a nice way of seeing an inclusion. You can say that an inclusion is a subset being a set being a subset of another, or you can see the inclusion as an ejective arrow from a set to another. Okay. I just give a name to these maps, to these inclusion maps. Okay, I have thickenings. Now I will triangulate them, or I will rather weak triangulate them. The thickenings are union of balls. I take the nerve up. I obtain the check complexes, right? The check complexes are simplicial complexes that are homotopy equivalent to the thickenings. And I still have inclusions between the check complexes. And also these inclusion maps become also inclusion maps between simplicial complexes. Okay. I have this. Now I will apply the ith homology functor, right? To obtain a persistence module. I pick any I, an integer, and I consider the ith homology groups of my simplicial complexes. Okay, and homology is a functor. It transforms simplicial complexes, but also simplicial maps. Okay, yeah. Yeah. You have to show that you can define simplicial maps here between simplicial complexes. Here, for the theory, it would have been better to use singular homology, the homology of topological spaces. But remember that in this summer course, we only study a simplicial homology. So yeah, we should have done that with singular homology, but it is the same idea. Basically, you well transform the simplicial maps, the inclusion maps, into linear maps between homology groups. Okay. And now, what do we have? The first row is the persistence module of the check complex of X, right? A set of vector spaces plus maps between them. Here, this is a check complex of Y, the persistence module associated to Y, okay? And what are these arrows here? They define an epsilon interleaving. Because we have, by functoriality of the homology, this diagram was a commutative diagram. So this diagram is also a commutative diagram, right? So we satisfy the definition of an epsilon interleaving. And we deduce that these two persistence modules are epsilon interleaved, okay? Epsilon where the Hausdorff distance between X and Y. Okay, now we will use the isometry theorem. If we have that the interleaving distance is smaller than epsilon, then so is the bottleneck distance. And we deduce that the bottleneck distance between this diagram is smaller than epsilon, and this is the stability theorem. At the beginning from Cohensteiner, Edelsbrunner, and Harrer. And I think it's not from 2015. I think it was before that, which says the following. Consider two subsets of, so this is a version of the theorem. Consider two subsets of the Euclidean space, build their check filtrations, build the corresponding persistence modules, okay? Suppose that they are interval decomposable, then the bottleneck distance between the persistence modules is smaller than the Hausdorff distance between the sets. Okay. So conclusion, this circle gives you this barcode. This sample, which is close to the circle, will give you a barcode which is close to the circle in bottleneck distance. And how did we prove that? We adopted an algebraic point of view, okay? We first computed the interleaving distance between the persistence module. And by isometry theorem, we deduced something about the bottleneck distance. Okay. And so, yeah, a word about this theorem. It is so important because it allows basically to use persistent homology in practice. Because what is the problem with combinatorial algebraic methods in practice is that they are very unstable. If you have one noisy point or something like that, you could obtain very different results. And in real life, of course, our data sets are not very clean. But if they are still close to the hypothetical, to the theoretical data sets, we obtain comparable results. Okay, we obtain a barcode at the end that reflects the barcode of the theoretical shape that we are looking to understand. Yeah, I can repeat the conclusion. I will even write it in the chat. Stability allows to use persistent homology in practice. Okay. Most of the time, combinatorial and algebraic methods are very unstable. And an example of unstableness is when we tried to compute last week the homology of our species by selecting a thickening. If we so there are thickenings which are of the good homotopy type, but for some values up, we obtain something really different. And you have observed it in the Betti curves. The Betti curves are very unstable, right? So this is really a difficult question, though interesting, to select precisely thickenings. In general, these kinds of methods are very unstable, but persistent homology does not suffer too much from noisy points. Does not suffer. Thanks to the stability theorem. Okay. So we can trust persistent homology in practice. Okay. This is the stability theorem. Can you explain what is the role of the epsilon in the epsilon interleaving using this example of the circle? Yeah. I can show you? Well, when I build these check filtrations of the thickenings, what I have are thickenings that are included one to another. I thicken a bit the circle, I can put the point cloud inside, then I thicken the point cloud, I can put the thickening circle inside, and so on, okay? I have here a collection of thickenings that are really close to each other, okay? I thicken the point cloud, it is included in a larger thickening of the circle, included in a larger thickening of the point cloud, etc. And the idea is that these inclusion maps will give me an epsilon interleaving between persistence modules. Okay. Really, this interleaving that we can build between the persistence modules is very simple. It comes from the inclusion maps, okay? And then we can use the isometry theorem to deduce something about the bottleneck distance. I can give you a more intuitive explanation. Basically, in practice, you cannot find this epsilon because the thing is that we do not know what is the circle. So you cannot compare your data set to the theoretical data set, to the theoretical shape. You cannot find the Hausdorff distance between your data set and the theoretical one. So what you assume when you do persistent homology is that the Hausdorff distance between your set and the theory is small. Yeah. So yeah, if your data set is too noisy or does not look like something interesting at all, persistent homology will tell you anything. I mean, won't be interesting. You have to suppose this. Well, though, so this is the first answer. You can still try to do statistics and ask whether my point cloud is close to an underlying shape. Because, for instance, manifolds, I didn't talk about that a lot, but manifolds are a class of nice shapes. They are very regular, and we can try to make statistical tests, such as, does my point cloud is sample close to a manifold? You can do stuff like that. So this is interesting. Yeah. But yeah, and so the explanation of this epsilon is that, well, in this in this thickening of my point cloud, I may have some topological noise, right? For instance, here we see a bit of cycles. I may have some topological noise, but it will disappear fast because we have to go through the circle at some point. Well, if I am here, say I have topological noise here, up, I'm going into the thickening of the circle, and this kills my topological noise, okay? So when we go back to the original persistence module, the cycle died. This is the meaning of epsilon. You can solve the topological noise can only survive epsilon over time. Yeah. You're welcome. So we conclude. I show you today how this topological noise that, so this is what we said yesterday. Topological noise correspond to small bars in the barcode, okay? We define the bottleneck distance, and this is a supremum of cost of matched pairs. So the bottleneck distance is not sensitive to small bars. It allows, the bottleneck distance allows to have topological noise. We show that it is equal to the interleaving distance. And this interleaving distance is very useful to do algebra. And so by mixing all of that, we deduce the stability result, which is the most important result in persistent homology theory. All right. So you can have a look at exercise 53. This was the last theoretical course. Tomorrow, so I prepared some data set. We will try to do that in practice because, okay, this was the math, but there is also a whole expertise, a whole knowledge of how to use persistent homology in practice. This is also very interesting. So I will show that to you tomorrow. Thank you very much.